This graph maps the obliquity of the ecliptic, Earth's axial tilt, over the past several millennia. The smooth curve is derived from Newcomb's formula, the standard retroactive mathematical model used by modern astrophysics to determine the position of Earth's axis at any given date in history. When we plot the actual physical measurements recorded by history's earliest astronomers, the data points systematically diverge from this theoretical curve. Pytheas of Massilia recorded a measurement in 326 BC that sits nearly 10 arc-minutes higher than what modern theory dictates for that year. Further back, Thales of Miletus recorded data in 558 BC that reveals a discrepancy growing to a full 15 arc-minutes. This creates a direct conflict between empirical record and modern theory. We must determine if these deviations represent a failure in our theoretical astrophysics or if they are simply the result of primitive measurement errors. Resolving this requires a rigorous metrological audit of naked-eye astronomy to test the exact precision capabilities of pre-telescopic instruments. If those ancient measurements prove accurate, our current understanding of Earth's orbital history is missing a massive, dynamic physical shift. We begin the audit in Egypt in 230 BC, using a geographic baseline between the cities of Alexandria and Syene. Eratosthenes made a foundational observation here during the summer solstice. He noted that a vertical gnomon cast zero shadow at noon, while sunlight traveled perfectly straight down to strike the bottom of a deep well at Syene. From this specific observation, Eratosthenes calculated a raw axial tilt of 23 degrees, 51 minutes, and 15 seconds. To audit this number, we have to account for the difference between measuring the precise center of the sun and its shadow-casting northern edge. Failing to account for the sun's outer edge creates an automatic angular distortion. The ancient astronomers recognized this, geometrically engineering their calculations to isolate the center of the solar disk. Today, metrologists test Eratosthenes' raw data by applying modern physical corrections for the sun's semi-diameter, for solar parallax, and atmospheric refraction. When these physical corrections are applied to his observations, Eratosthenes' calculated latitude for Siene matches modern satellite data to within 38 arcseconds. This level of accuracy means the 8-minute deviation between his obliquity data and Newcomb's formula is statistically significant. It falls well outside his demonstrated margin of error. The geometric rigor of the Greeks forces us to take the oldest data points of the obliquity anomaly seriously. To push beyond the limits of human visual acuity before the telescope, 16th-century astronomers turned to a mechanical solution, scaling the physical architecture of their instruments to the size of buildings. The parallel observatories of Taki al-Din in Istanbul and Tycho Brahe in Denmark represent the mechanical limit of naked-eye data collection. Their primary tool for measuring stellar altitude was the mural quadrant, bolted permanently to a wall aligned with the meridian to eliminate alignment error. Tycho Brahe constructed a quadrant with a radius of 2 meters. Taki al-Din scaled his instrument even further, building a massive 6-meter radius quadrant in Istanbul. Expanding the radius of an arc proportionately increases the physical distance between the degree markers. Inside those widened gaps, they used the transversal point system, a geometric grid that subdivides a single degree into a precise matrix. This combination of architectural scaling and transversal grids allowed visual readings down to resolutions as fine as 5 arcseconds. By building instruments of this scale, these astronomers entirely eliminated the physical possibility of a multi-minute observer error. In metrology, high resolution requires redundancy. Measurements must be verified across different tools. Both observatories relied on the armillary sphere to map complex celestial latitudes and longitudes. This is the 4-meter multi-ringed armillary sphere used by Taki al-Din. This identical instrument was engineered independently by Brahe in Europe. To measure lunar parallax, they used the triquetrum, or parallactic ruler. Here is the triquetrum in operation at the Istanbul Observatory. Its foresight was sized to cover the visual disk of the moon, locking the alignment in place before a measurement could be taken. The final verification tool, developed simultaneously in Istanbul and across Europe, was the observational clock. By tracking exact sidereal time, These astronomers could verify spatial arcseconds by measuring the elapsed temporal seconds between celestial crossings. These 16th century observatories were rigorous, multi-axis data collection engines that produced unassailable records. The mathematician Johannes Kepler inherited Tycho Brahe's heavily audited dataset. When he compared Brahe's accorded observations of Mars against the accepted theoretical models of the time, he found an 8-minute discrepancy. Kepler faced a choice between trusting the centuries-old Platonic theory of circular orbits or the physical instruments Brahe had built. Kepler declared that Brahe was too skilled an observer and the instruments too precise for an 8-minute error to exist. Trusting that 8-minute anomaly forced Kepler to abandon circular models, leading directly to the discovery of elliptical orbits. He established a precedent. When audited, verified empirical data contradicts established theory, the theory must break. Returning to the obliquity anomaly, we place the historical observations side by side with Newcomb's modern formula. The graph displays a persistent 8 to 15-minute gap spanning from Eratosthenes to the 17th century. Our audit confirms that the architects of pre-telescopic astronomy operated with verified sub-arc-minute capability. As Kepler did with Mars, we can no longer dismiss this gap as a symptom of primitive engineering. The data suggests Earth's axial tilt experienced a physical, dynamic shift in the past that current retroactive models cannot account for. The records left by these historical observers serve as a precise empirical footprint of a moving Earth, evidence that challenges modern astrophysics to catch up to the past.